So far with exponential functions in the context we've seen, we've only looked at where it makes sense to put zero or positive inputs into our function, but we want to generalize these exponential functions as we have with our other function types. In this video, we're going to specifically focus on the graphical representation of these exponential functions, their end behaviors, and specific features of their graphs. The setup for this conversation is the same form of the exponential we've already talked about, where we have a times b to the x, where a is this initial amount or the starting amount, or what you get out when your x value is 0, and b is this growth rate. Whether this will be an exponential growth or an exponential decay function depends solely on the value of this factor b right here, this exponential factor. As I throw through some details here, importantly, I'm only going to consider where a is positive. A could definitely be negative, but we'll think about that in a future video and talking about that as a vertical flip, as a transformation. So let's consider only a positive here. B then also always has to be positive for an exponential, and it can't be 1, or again, it's a constant function. First, for me, I think the two most important grounding points of the graphical representation of the exponential functions are a couple points. First of all, we have the vertical intercept, which we know already. It's this initial value a. When we plug in a 0 for x, this factor, goes to 1, and we just output this. So importantly, for every exponential function of this form right here, we have a vertical intercept at 0a. And then I personally like having a second point. Again, this will help with the conversation of do I have a growth or a decay model and looking at the representation, is I think about what happens if you plug in a 1. So if you plug in a 1 into this function right here, what you're going to get is just a times b. So that will always be a second point. And so we'll just say 1 comma a times b is a second point. And to clarify that, why I like this second point is that when you look at a times b, or the initial value times that growth rate, then it's very, very clear whether you have an increasing or a decreasing function. So you have the starting value, and then if this multiplication is greater, then your function is increasing between 0 and 1. And if this value is less than, it means you have a decay model and it's decreasing. Before we go any further, let's look at our first example here of a growth exponential model. F of x equals 10 times 3 to the x. And as you'll see here, I've denoted these 2 points on this graph. At 0a, a in this case is 10, so we have the point 0, 10. And the second point we've noted is at 1 comma 30. And again, the 30 comes from the 10 times the 3. Then importantly, if our b value, our exponential factor here, is greater than 1, then we know this represents exponential growth. But graphically, what that means is that then f of x is strictly increasing. And then graphically speaking, if we had the case where we have an exponential decay model, that would be strictly decreasing, because as we increase the independent variable, the outputs are going down. So in this case, then f of x is strictly decreasing. So let's now talk about negative inputs in this context. Importantly, when you look at the graphical representation of f of x here, you'll notice something interesting as we input negative values, or bigger and bigger negative inputs into our function. This function steadily goes to 0. And in fact, with all exponential functions, we'll have this feature. And the reason for this feature is that as we take 3, and we use bigger negative exponents, so something like 3 to the negative 10. If you remember, negative exponents represent this reciprocal. What happens is this factor right here that you're multiplying by, no matter your starting amount, but this gets so small, for instance, 3 raised to the negative 100 is 1 over 3 to the 100th, an incredibly small fraction, is that this exponential factor for larger and larger negative inputs makes the output go to 0. But importantly for exponential functions, and this is different than many of the functions that we've seen, like rational functions, is that this function only obeys that horizontal asymptote for the negative inputs. So importantly to reiterate, for any exponential function of this form right here, we'll have a horizontal asymptote at y equals 0, but the graph doesn't obey that horizontal asymptote from both directions. It will only be the negative or the positive direction, or as we go to negative infinity or positive infinity. When we have a growth model where we're an increasing function, where we're swooping like this, as this example right here, we obviously aren't going to approach the horizontal asymptote as we get infinitely positive large numbers, but as we get infinitely negative large numbers, we do approach that. So importantly here, we have end behavior. And again, this general end behavior that I'll talk about is generally for any growth model that hasn't been transformed. So the end behavior is as x approaches infinity. So as we go, we increase the x value in the positive axis, our function will also go to infinity. And then as said, if we instead approach negative infinity, so we go across this x-axis in the negative direction and keep going, our function will approach that horizontal asymptote at 0. And then for our list, the final thoughts are domain and range. Our domain, again, which are the values that we can input, as always, given a function of this type right here and no context, we'll have all real numbers. We can input whatever we want into that exponent. So it could be negative infinity to infinity, or we could just denote that with all real numbers. The range is a bit different, more different than that. We won't actually output all values. And in fact, when you look at this, given this nature, given the fact that this is strictly a positive growth factor, and we are considering the case where a has to also be positive. 0. And you'll see here what that does in this context is it makes the range or the outputs of this function strictly positive. This function cannot output 0 or a negative numbers, and that is the case with all functions with this setup right here. And so our range is strictly positive numbers. All right, so then it makes sense to look at an exponential decay model with this same analysis. Here I have g of x equals 30 times 1/3 to the x. I know this is exponential decay because this exponential factor here is between 0 and 1. This is going to make this a decreasing function or exponential decay. And as you see here, it's what we'd expect is as we move from left to right, this function is slowly decreasing. We also see the points that we've identified here. We have that vertical intercept that we've talked about that comes from this a value. So we have the point 0, 30, which is our starting amount when x is equal to 0. And then we also have this second point. And again, I really like looking at this second point at x equals 1, just because it helps me verify this growth versus decay, gives me some grounding if I'm going to graph this with transformations and such. But I have 1, 10. And again, that 10 it comes from the 30 times the 1/3. And importantly, when you look at this function, this looks like it's a horizontally flipped version of the type of graph that we looked at before. And in fact, it is, and I'll talk about that in 1 second. There is a very important connection between growth models and decay models and this idea of reflection. But importantly to the conversation of end behavior here, we can see again that we have this horizontal asymptote, but it's not being respected as x goes to negative infinity, only positive infinity. So importantly here is as x approaches negative infinity, we go to infinity. But then as x approaches infinity, this is in this decay model, our function value goes to 0. So when thinking about the graphical representation of these exponential models, again, importantly, the one first thing you look at is it a growth or a decay model? Is this b value bigger than 1 or between 0 and 1? But with whether it's growth or decay, we get these first 2 points, but they should verify that thought. Is it increasing or a decreasing function? And then for all these exponentials, we do have a horizontal asymptote that affects our end behavior, but it's only on one half of the graph, either as we get big positive or big negative. And in this case, when we have a decay model, we should expect that the function goes to 0 as we increase our x values, right? Because if it's decaying, as we increase time, let's say, the output goes to 0. The opposite's happening as we go to negative infinity, the function's values are getting infinitely large. And I just want to talk too about this relationship between a decay model and a growth model. And this will help us with the next conversation we'll have in a little bit, which is about the transformation of these types of functions. But if I rewrote this as 30 times, instead of writing this as 1/3, I can write this as 3 to the negative 1 using the properties of negative exponents. And then I can use the properties of exponents to say to multiply these together. What I get is a way of thinking about this as a horizontal flip. So we have this negative being applied to the input here. So if I was thinking about the function 30 times 3 to the x, that's clearly a growth. So if I didn't have a negative here, and all this graph is that graph of 30 times 3 to the x, and then horizontally flipped. And all I'm trying to show with that thought right there is illuminate the idea that we can apply transformations to these functions also, but also the fact that this exponential, the shape of an exponential graph is exactly the same whether you have growth or decay. Really, the only thing is this perspective, which has been flipped horizontally, is are we exponentially increasing as we increase our inputs, or are we exponentially increasing as we put in larger and larger negative inputs? Though we rarely think about it like that, what we actually usually only think is from the perspective of increasing the independent variable. And again, in this case, because of this flipped nature of this exponential, this, as we increase our independent variable, where our function is decreasing and going to 0.